Okay, everyone, in this video, I want to summarize some conclusions after working through a couple of examples in the previous videos, and then see how we can apply this to some examples that I have on the last slide. So we've looked at 3 examples in some of our earlier videos, and up top I have kind of the resulting reduced row echelon form that we got for each of those augmented matrices. So if I'm given a linear system of equations, right, we start with the augmented matrix. We perform these elementary row operations to obtain an equivalent reduced row echelon form. And if I notice, and I'll notice this even before I try and reduce it, that after putting the matrix in row echelon form, if we see that the rightmost column in the matrix is a pivot column, that's going to imply that, such as in example 3, that we're going to wind up with some equation which is false. That is going to tell us that 0 is equal to 1. So if I ever have a matrix that has a pivot column way on the right, then that's going to tell us that this system has no solution. So this most recent example that we did, we had a pivot column in the first column, we had a pivot column in the second column, we had a free column over here, and then the last column was a pivot column, and that's what led to an inconsistent solution. We had no solution. In these other 2 examples, they were both consistent. So for example 1, we had a pivot column in the first column, the second column, and the third column. And so we had no free variables in that example, so that gave us a unique solution. In example 2, we had a pivot column for x1, we had a pivot column for x2. Over here, there was no pivot in this column, so this was a free variable over here. So this is an indication that we have an infinite number of solutions. So if there is no pivot in the rightmost column, our system is going to be consistent. So then we should go ahead and make sure that we express this matrix in reduced row echelon form like we've done over here. And after we have it in reduced row echelon form, we then can extract what the solution set is going to look like. So when every variable has a pivot in its column, that's when we have a unique solution. So this would tell me x1 is 1, x2 is 1, x3 is 2. When we have a free variable like this, then what we want to do is go ahead and rewrite each of these equations out, which I've done below. So from the top row, right, we would have x1 plus 7x3 is equal to minus 8. From this row, we get 1x2 minus 3x3 is equal to 3. And then what we saw is that it's useful to actually go ahead and write the solution as x1 is equal to this, x2 is equal to that. And that I've written out over here on the right. So this would have a solution, x1 is equal to minus 8 minus 7x3, x2 is equal to 3 plus 3x3. So in here we have an infinite number of solutions. For any value of x3 that I pick, we can generate a solution. We can figure out what the corresponding x1 and x2 values would need to be. Okay, so on the last slide, I have a couple of examples to kind of test our understanding of what we can infer from the reduced row echelon form of a matrix. Okay, so let's take a look at a couple of examples. So let's imagine I'm working with a system of linear equations, and that augmented matrix for that system is row equivalent to this reduced row echelon form matrix over here. So you may just want to verify this matrix is in reduced row echelon form, and I'm just highlighting each of the pivots. So we have 3 pivots in this case. And for each of these pivots, this corresponds to a basic variable. So x1 is going to be a basic variable, x3 is going to be a basic variable, and x4 is going to be a basic variable. These columns that do not have a pivot, these are going to correspond to free variables. So I can see that x2 is free and x5 is free. So this tells me right away, before I even write out the solution set, that here we have an infinite number of solutions. And what's going to be useful would be to write out these solutions in terms of each of the basic variables. x1 equals this, x3 equals this, x4 equals that. So let me write out each of these equations. And so this first set in red, that's just writing out the corresponding linear system for this augmented matrix. And then what I want to do is solve for each of these basic variables. So I can solve this equation for x1. This gives me the relation between x1 and these free variables x2 and x5. X2 is free, that there's no pivot in column 2. Here's the corresponding condition for x3. Here's the condition for x4, and x5 is free. We can pick any value that we want for x2 and x5, and then once we pick those values, we can determine what x1, x3, and x4 would have to be. So this first matrix corresponds to a consistent system, and we have an infinite number of solutions for that system. For the second matrix, let's first identify where the pivots are. So we have a pivot in column 1. We have a pivot for column 2. We don't have a pivot in column 3 or 4, but we do have a pivot in the last column. So from this, we can see that we would have a couple of basic variables like x1 and x2. We have a couple of free variables like x3 and x4. But in this case, we have this problem where the rightmost column has a pivot. And when that happens, that tells me we're going to wind up getting an equation from, say, this last row that says like 0 is equal to 1. And so this is false. And so when we have a pivot in the rightmost equation, that leads to a contradiction. And this tells us that we have no solution to this system. This system is inconsistent. Okay, so hopefully this series of lectures you focused on how do we apply this row reduction algorithm, this Gaussian elimination. And once I've got the matrix in reduced row echelon form, how can I then say something about the solutions?